I will start off class by reiterating some things that I sent out in a previous email that I sent out yesterday. So to go off of this email, as I mentioned, classes resume today, so hopefully you've all figured that out by now. So the assignment due dates, I went ahead and changed at least the homework and the quiz that were coming up for quadratic equations. So for quadratic equations, that homework was due tonight, but now it's due tomorrow night. And then the quiz was pushed back a day as well. Additionally, now that means that the quiz and the workbook are on the same day, but to really to make up for that, so I wrote it down here. It may seem like a lot of workbook pages, but the tutor's going to work out all of them. So you show up to Friday's session, and the tutor's going to work out all of these problems. So whoever your tutor is in that session, they're going to work out these problems. So, so if anything, that'll be less work on your end. So I'm still getting emails about the workbook. Some people still don't have it. So I'm going to just keep emphasizing you have to get it from the bookstore. It's been a month, so you really need to get this book by now, or you can get it online, and I give the link to the specific item in the online bookstore. So you really need to get that. Additionally, somewhere where you can be a little bit proactive, or just let me know this as soon as you can. If you want to take the midterm remotely instead of in person, because the midterm will be coming up in 2 weeks. So if you want to take the midterm remotely instead of in person, just shoot me an email by Monday and just let me know. Just say, I want to take it in person. And later this week, I'll send you instructions on how to facilitate that. Now, this is going to be through something called ProctorU, the third-party proctoring service. Some things that may influence your decision on whether to take it in person or online. It costs $20 if you take it through the proctoring service. Regardless, the midterm is going to be taken depending on which group you're in. So it's taken during class time. So if you're in group A, you're going to take the test Monday, September 28th. If you're in group B, Wednesday, September 30th. This is mainly based off of your last name, unless you asked to be in a different group for whatever reason. So whichever group you're in, just that's what time you will take the test. In-person testing is going to be in the Sims library, and again, this is all stuff I'll explain next week. But these might be things that influence your decision on using or taking the midterm in person versus through ProctorU. And I suppose, oh, I'm sorry. Okay, you're definitely right. You're definitely right. All right, okay. I copy and pasted from my previous class. Let me back up. It is during class time. That's my fault. Yeah. So that should not say 8 a.m. I got caught copying and pasting. So it should be during your class time, 9:30. So I hope I didn't scare anybody through that. So that should be at 9:30, not 8 o'clock. I'll send an update after class. But yeah, definitely right. So midterm should be during class time, 9:30. So okay. So what I also wanted to say was, in regards to ProctorU, I do want to emphasize that ProctorU is, and taking the test online, if you're planning on using it as a way to sort of cheat the system, then I don't really recommend it. ProctorU, if you know anybody who's taken or who has used ProctorU, you might want to ask them about their experience with it. It's a fairly tumultuous process to get started. It tends to be a little, I suppose, it's not the most straightforward, or I'm trying to think of the right words to use. some people may not have had the best experiences with ProctorU. And so if you can avoid using ProctorU, I'd probably recommend it. But you do have to show them your, they do verify your identification. They do go through this tedious process to make sure you have no materials available. You have to have a webcam available and all of these things. And your computer has to pass these certain requirements. I'm not trying to tell you you shouldn't use it by any means, but if you're just trying to use it to, say, cheat the system and you think, all right, I'm going to have someone take my midterm for me, it's not going to be that easy. So that's just another thing to consider to influence your decision. Now, if you're just taking it, genuinely and you don't have any issues with that, then by all means, ProctorU will be just fine. But I just wanted to give you a heads up. So yeah, you take it during class time. So 9:30 and not 8 o'clock. So ignore what I said in the email here. It shouldn't be 8, it should be 9:30. Other than that, yeah, again, all that information, pretty much all that information is here in the email. And all right, after that, I suppose we can go ahead and move on to the material at hand. So we're going to move on to radical equations, which the corresponding homework will be due on Sunday. So we'll look at radical equations now. So radical equations are, well, they are equations that have radical signs in them. What's a radical sign? It's any sign that involves a root of any kind, a square root, a third root, a fourth root, something like that. So a radical expression is just anything with some sort of root. Like I said, a second root, a third root, a fourth root. The umbrella term for all of those is a radical. The number of the root, so I think there might be a homework question or two about some terminology. The value of the root is the index. So if you're taking the square root, the index is 2. Taking the third root, the index is 3, and so on and so forth. And the number under the radical symbol is called the radicand. So I've mentioned that briefly before, but the number underneath the radical symbol is the radicand. More importantly is this way of converting back and forth between radical notation and a base with a fractional exponent. Sometimes throughout this section, in fact, quite a few times, we will be converting back and forth. So if you have a fraction as an exponent, then this is a way of writing that fraction exponent as a radical. And sometimes it's easier to look at things as radicals because a particular form might elicit a particular process in our minds about how to proceed, which you will see later. So we can move on to example 1 here, and we are going to simplify these following radical expressions. So with problem 1 here, you might be tempted to think, all right, you might be tempted to think, all right, I see a square root and a square, so don't they cancel? And really the answer is no, because there is some sort of algebra we have to play up to. So the answer to this is not -8. So really what's happening here is everything under the square root, called the radicand, that needs to be evaluated first. That is associated together first. So everything under the square root, we need to evaluate that. So -8 in parentheses squared, put that in your calculator, you will get +64, which is what you should get. And then from here, we can take the square root of 64, which is +8. So really, this is the correct process to go about simplifying this. And so for problem 2, it's the same idea. You would first evaluate what's under the fourth root in this case. So you're not canceling out the fourth root and the 4. You want to go ahead and evaluate -2 raised to the 4th power, which you should get positive 16. And then from here, now it's a matter of, well, what is the 4th root of 16? And you can actually do that in your calculator. So this might be new for some of you. The way you would do a 4th root, and I'm just going to write it out here. The way you would do a 4th root in the calculator, if everything's clear, so for this calculator, the class required one, press 4, second, and the caret symbol, which will give you the special looking root. So far, virtual people, you should have something like this. And then you could type in 16. And you should get 2. Or in other words, what number multiplied to itself 4 times will give you 16? It's 2. If you cannot figure this out, try to make sure you typed in everything correctly in your calculator. And if you need help trying to figure it out, we can talk about it after class. Let's move on to problem 3 over here. So this has 64 to the 1/2. So the issue initially is, well, there's no radical. So there's no radical, there's no root symbol at all. But it turns out there is a root symbol there. It's just not written in that manner, and we have to convert it using this conversion that we talked about earlier. So how this conversion works is what this says is the denominator tells us the root. The denominator of the exponent tells us the root. The denominator of the exponent is a 2. So that tells us we have a second root or a square root. What are we taking the square root of? The 64 raised to the 1st power, because there was a 1 in the numerator. And then the square root of, well, what's ideally 64, the square root of 64 is 8. So really, problems 1 and 3 are the same problem, almost. So from here, so let's look at another one like that. Number 4 over here. The denominator of the fraction in the exponent will tell us the root. So the 4 is the denominator of the fraction in the exponent. So that tells us we're taking the 4th root. What are we taking the 4th root of? 16 to the 3rd power, because there was a 3 in the numerator of the fraction in the exponent. So what's 16 to the 3rd power? 4,096. And then using the calculator method I mentioned above, up here, we can do the same thing to figure out the fourth root of 4,096, which is just 8. So I guess the question now is, well, what happens if they throw a negative symbol, or rather if we have a negative exponent? So what happens in that situation? What does a negative in the exponent mean? And so what that means is whatever your base is, whatever the base number is, which is the 216 in this case, you are going to flip it. That's it. So the 16 here will be flipped. And what that means is that will become 1 over 216. So notice 4 over 3 is no longer negative, it's positive. So negative 4 over 3 becomes positive 4 over 3 now that we flipped the base. That's what it means to have a negative exponent. You flip whatever the base number is. So the 4 over 3 is still there. Notice the negative sign is gone now. And so now, so the issue is if you try to find the third root of all of this to the fourth power in the calculator, it will not give you an answer. So trying to put this in the calculator now, it's going to be way too small of a number. Calculator is not going to interpret it correctly. Instead, what we need to do, so we have a fraction raised to an exponent. So that means the numerator and the denominator both get their own exponent. This is just a basic algebra property. A fraction raised to a power is the numerator and denominator both individually raised to that power, as I did right here. And we'll see this in the next problem as well. So this is the third root of 1 to the fourth power. And this is the third root of 216 to the fourth power. So 1 to the fourth power is 1. The third root of 1 is just 1. And then you can do the same thing for the bottom. 216 raised to the fourth power is a huge number. Taking the third root of that number is going to give you 1296. This is slightly more complex to make sure you can put it in the calculator correctly. And if not, you could just ask me after class or email me about it. Let's look at number 6, and then I'll ask you all if you have any questions about anything. So problem 6 here. We have a fraction. Well, if anything, we have a fraction raised to an exponent. So if anything, we'd like to split it up before anything else. So this is negative 27 raised to the 2 over 3 divided by 216 raised to the 2 over 3. Like that. So the numerator gets its own exponent, the denominator gets its own exponent. This is just a basic algebra rule. So really, what this is, the numerator is the third root of negative 27 quantity squared divided by the third root of 216 squared. So hopefully you can put both of those in the calculator and figure it out from there. So what you should get is 9 for the numerator. Negative 27 squared is 729. And when you take the third root of 729 in your calculator, you would get 9. The third root of 216 squared, or 216 squared, 46,656. And then when you take the third root of that, you get 36. So you should get 9 over 36, which does simplify to 1 over 4. So it simplifies to 1 over 4. Does anyone have any questions about any of these simplification ones before we continue? If you're having any calculator difficulties or anything, you could just ask me after class. We'll go ahead and move on to radical expressions or equations. And I do give a note as we solve these. So we saw this actually in the previous section when we had to check our answers whenever we had fractions with variables in the denominator. We have a pretty similar situation here. If an equation has an even root, and I list off a square root, a fourth root, a sixth root, so even numbered root, please check your answers. So pretty much that. If you have an even root to start off your problem, you need to check your answers. Some of them may not work. Let's look at problem 1 here. So these are radical equations, which means now we can solve, which means our final answer should be x is equal to something, or possibly no solutions. So for this first problem here, the first thing we need to do, well, the problem here is that x is stuck underneath this radical symbol. It's stuck underneath a square root. So how do you get rid of a square root? You would square both sides. A square gets rid of a square root. So the square root and the square cancel, and then on the other side is just 4 squared, which is 16. And from here, it's just a standard linear equation. So now we ask ourselves, do we have to check this answer? The answer is yes, we do need to check it. And so that might raise a question of what does it even mean to check an answer? What does that even mean? What that means, so when you check an answer, what you're doing is plugging in that x value. You're plugging that x value back in, and you're seeing, does the equation actually make sense? So if I plug in x, 6 for x, will I end up getting 4 as the answer? So what I end up getting is 24 minus 8, which is 16. Square root of 16 is 4. So I do get a consistent equality here. So we checked it, and it actually works. So that one's good. Example 2 is fairly similar. It takes up the difficulty a little bit. So our thought process before was the variable was stuck underneath a radical, so we needed to square both sides. We do not start off this problem by squaring both sides. The reason why we were able to do it in problem 1 is because it was written in a pretty convenient form. Now, in this section, the first thing you have to do is isolate the radical. So you got to isolate the radical. That's the first step here. In problem 1, the radical was isolated. Problem 2, there's this pesky -3 in the way. So all we have to do is add 3 on both sides right quick. And then once we add 3 on both sides, so -12 plus 3 is -9. So now the radical is isolated. It's by itself. There's no other numbers adding or subtracting to it. So that term of the square root is isolated. Now, from here, we could proceed. So from here, it's now the exact same type of problem as the previous one. However, perhaps the more astute student may see why we can just stop right here. I mean, if you don't see it, that's fine, and I'll kind of loop around and explain what it is. But someone might be able to look at this form and think, all right, it's no solutions for some reason. We'll get to that reason here in a bit. Let's just pretend you didn't even see this. So I'm going to rewrite it. And now the question is, all right, so since we have the radical isolated, we can go ahead and get rid of the radical by, well, it's a square root, so we square both sides. Square root and the square cancel. And -9 quantity squared is +81. So we end up getting that t is 9. And so the question now is, do we need to check the answer? We do need to check the answer because the problem started off with an even root. So we need to check this. So the problem we had was the square root of 8, well now times 9, plus 9 minus 3. And now the question is, does that give us the -12 that was over here? So does that give us -12? Well, let's work it out. So this is the square root of, let's see, that's 72 plus 9, that's 81 minus 3, which is 9 minus 3, which is 6. Oh, that's interesting. We got 6. Got 6 when we were supposed to get -12. That means that we reject this answer. So we reject it. And since there's no other answers, we would conclude with no solutions. That's the true answer here, no solutions. We rejected the only answer that we found, which means we have no solutions. So now the question lies, so I was able to predict this after just one step. I apparently was able to predict this here. Question is, how was I? What made this so much different than the previous problem? The reason is because the square root, a square root cannot output a negative number. The output of a square root cannot be negative. Before we had +4, and that was okay. Here we have -9, and there's no way to take the square root of a number and get a negative number. So in general, even roots don't really like negative numbers too much. Even roots don't like to input negative numbers. Even roots don't like to output negative numbers, which is why we have to be so particular about them. Odd roots, on the other hand, do not care. You do not have to check your answers with odd roots. They just do not care at all. You can have negatives, positives, 0, whatever you want. So this is sort of the slow motivation towards why this is the case. But we'll do some more examples after this. In the meantime, does anyone have any questions before I proceed? If not, let's go ahead and move on to example 3, which are fairly similar problems. So we'll start off with part 1 here. So it's the same premise as before. We're going to solve. And with part 1 here, well, our thought process would initially be, well, there's a variable underneath a radical symbol. How do we get rid of the radical symbol? Well, it's a third root, so we need to take a third power. But we're not going to take a third power yet. We need to get the radical by itself. The radical is not by itself. This pesky 5 is in the way. So we cannot just apply a third power to get rid of a third root. So let's go ahead and subtract both sides by 5 right quick. And by doing that, well, we have 2 minus 5, which is -3. Now the question here, we're at a form that was fairly similar to the previous problem, except instead of a square root, we have a third root. Now the question is, can we just stop right here and say that there's no solutions? We cannot. Third root doesn't have any particulars to it. If this 3 was just simply gone, then that would be a square root. And we could stop right here and say no solutions, because square root cannot output a negative. But since it's a third root does not care. So we have to keep going. We cannot make any determination. So I'm just going to rewrite it. And so to get rid of a third root, we need to apply a third power. Which would cancel out. And we are left with 4x minus 7 is equal to, well, -3 raised to the third power, which ends up being -27. So it goes back to a linear equation. We can add 7 on both sides and divide by 4. And we end up getting that x is -5. Now we ask ourselves, do we need to check this answer? We do not need to check this answer. We only have to check answers. We only have to check answers whenever there are even roots involved. This is an odd root, third root. So we do not have to check any of the answers. This is good. So we just conclude with this. We don't have to check anything. So we'll move on to problem 2 here. So another radical equation. We ask ourselves, all right, so do we need to isolate the radical, or is it already isolated? And the answer here is it's already isolated. The radical, the square root, it's already by itself on one side of the equation. So from here, so this is one square root. This is one radical. So we do not, it's already isolated. So that part's already clear. The next part is, well, once we isolate the radical, well, you might look here as we did before and ask, for a fifth root, can that output a negative? Well, yeah, it can. Only even roots are the ones that we have to worry about. This is okay, and we keep going. How do we get rid of a fifth root? We apply a fifth power. So a fifth root and a fifth power cancel. We're left with x squared plus 18x is equal to, well, -2 to the fifth power, which is -32. And so you might notice this is close, this is very close to a quadratic. In fact, it's so close, all we have to do is just add 32 on both sides. And by doing that, we now have this in standard form. This now becomes a problem from the last section, which happens. You could end up simplifying a radical and then run into a quadratic expression. And now we can factor it like we did before. So two numbers that multiply to give us 32 and add together to give us 18. Thinking 16 and 2. So then we get x is equal to -16 and -2. Now the final thing we ask is, do we check our answers? The answer is no, we do not need to check our answers. These both will work by default because we had an odd root to start off the problem. So odd root, don't have to check the answer. So let's move on to problem 3. The first thing we ask ourselves, is the radical isolated? The answer is no. The 4 is in the way. But we don't subtract both sides by 4. We divide both sides by 4. Because 4 is multiplying the square root. So we would divide both sides by 4. Because again, 4 is multiplying the square root. It's not adding or subtracting, so we need to do the opposite operation. And then from here, now we have x divided by 4 is equal to the square root of x minus 4. And now the square root, the radical, is isolated, which means we can go ahead and get rid of it. So how do we get rid of a square root? We square. So the square root and the square cancel. So x divided by 4 squared, that means, like we talked about before, we have to square the x and we have to square the 4. So that's why x in the numerator becomes x squared and the 4 in the denominator becomes 16. It's because we have to square both of them. But then on the right-hand side, the radical cancels out. So from here, now we have a problem from the previous section where we can go ahead and apply the least common denominator, which is 16. So multiply everything by 16. We get this. So this is to get rid of the fraction. And now by moving everything to the same side, now we have a quadratic in standard form, which means we can factor it. So exponents in descending order, set that equal to 0. So we can go ahead and factor. And I see -8 and -8 2 times. So two numbers that multiply to give positive 64, -8 and -8, and add together to give -16. And from here, we will get that x is 8. Finally, we ask ourselves, do we need to check that answer? So we do need to check the answer. And it turns out that this answer ends up working. Here, the problem was x is equal to 4 square root of x minus 4. And then we found that x was 8. And it works. By plugging 8 back in, we get that we do get, in fact, an inequality that makes sense. So this one works. Okay. Does anyone have any questions up to here? If not, let's move on to problem 4 over here, which may look a little different because there's no radical. But it turns out there actually is a radical to this problem. So the radical here is the fact that this is the exact same as, well, what happens if we rewrite this as a radical because it has a fractional exponent. The 2 in the denominator tells us that we're going to have a square root. And then a square root of 3x plus 3 to the first power. Really doesn't do anything. Let me rewrite that. So the square root of 3x plus 3, all that's equal to x. So now we do have a radical. So we did have one, it just was not written in that form at first. Now from here, we ask ourselves, is the radical isolated? The answer is no, there's a 5 in the way. So we need to subtract 5 on both sides in order to get the radical by itself. what we have to do next was we did before. Now we can get rid of the radical by, well, this is a square root, so we can square both sides. Square root and the square cancel, leaving us with 3x plus 3 is equal to x minus 5 quantity squared. And we need to FOIL the x minus 5 squared. So on one side, we still had the 3x plus 3. And on the other side, we now have x squared minus 5x minus another 5x plus 25. Try to write that a little bit better. So 3x plus 3 is equal to x squared minus 5x minus 5x plus 25. There you go. And additionally, we have like terms. These 5x's right here, they can go together. So now that's 3x plus 3 is equal to x squared minus 10x plus 25. And additionally, we have more like terms because we could subtract 3x on both sides and subtract 3 on both sides. In other words, we're trying to put this into standard form. So negative 10x. So the negative 10x minus the 3x minus 13x. And then we have plus 22 because we have plus 25 and minus 3. So 25 minus 3 is 22. And so we can factor x squared minus 13x plus 22. It's going to be x minus 11, x minus 2. Negative 11 times negative 2 is positive 22, and their sum is negative 13. And from here, we get that x is 11 and 2. And now we have to check our answers. Because we started off with a square root in the beginning. So we need to check. Now I'm going to start off with x is equal to 2. So for x is equal to 2, 5 plus 3 times 2 plus 3 to the 1/2 power is equal to 2. So the very beginning of the problem, very beginning, all the way up here, I'm just plugging in 2 for every x value. And if you work this out, that's going to be 5 plus, well, 3 times 2 is 6, plus 3 is 9, to the 1/2 is equal to 2. 9 to the 1/2 is 3, and 5 plus 3 is 8. So then you get 8 is equal to 2. Oh, interesting. So you get something that is not true. So that means you would reject 2. And if you did the same thing for 11, you would end up getting that 11 works. Does anyone have any questions? Yes. How did they get 25? So backing up a little bit. So I got the 25. So when you FOIL, -5 and -5 in the FOIL, their product. So -5 times -5 is +25. Which, yeah, that's where that 25 comes from. The -10 comes from the, well, you see where the -5s came from, the -5x's, or, so it's just like terms between them. -5x minus 5x, that's a -10x. That's just combining those two together because they're like terms and they're right next to each other. So hopefully that provides a little bit more insight. Any other questions? If not, let's look at example 4 here. Find the real solutions of this equation. And so this one's a pretty tricky one on the homework, so I definitely wanted to talk about this one. So I'll go ahead and rewrite it. So the issue here, well, the first issue we have is that, well, I don't see any radicals immediately. I don't see any square root symbol, cube root, whatever roots. So let's go ahead and make them. Because anytime you see a fraction as an exponent, you can make a root. And you can do so. Remember, it's always the denominator that tells you what kind of root you can have. So this would be the square root of x to the third minus 67, and then the square root of really x to the first, which is just x. So if anything, we're rewriting these with radicals. And notice that 67 is not a part of the square root because we don't have 67 raised to the 1/2. So from here, the problem lies in, well, in the previous problems, we only had one radical and we isolated it. In this problem, we have two radicals. How do we isolate them? It's not the most straightforward question when propositioned in that manner. So what I would suggest, we're going to add the 67 square root of x to both sides. And the reason I do this is because really we do have pretty much isolated radicals here. Now the 67 we'll just have to deal with because since there's more than one radical, this one gets a little bit trickier. So there's no way we can really get rid of that 67 unless we did something really tricky. So instead, we're going to say this is good enough, and now we're going to get rid of the radicals. And the way we get rid of the radicals, so I'm just going to rewrite the problem. To get rid of square roots, we have to square both sides. So we're squaring both sides. The only thing to keep in mind is that we do have to square the 67 as well. So everything gets squared. So really the 67, we have to address it here since we couldn't really get rid of it to isolate the radical. So we do have to square the 67. So let's write down what everything looks like afterwards. So now we just get x to the third, now that the square root and the square cancel, is equal to whatever 67 squared is, which seems to be 4,489. And then the square root and square cancel to just leave x. So now we're here. From here, we can go ahead and subtract 4,489x on both sides. And the reason why is to get this as a polynomial in standard form, so we can try to factor and stuff. And that leaves 0 on the other side now that we moved everything from one side. So now the convenience of moving that term over is now both of those terms on the left have an x in common that we can proceed to factor out. And factoring is good because each individual product in the factorization will be now individually set equal to 0. So the x is equal to 0, and x squared minus 4,489 is equal to 0. That's the good thing about factoring, is we can break up bigger pieces or a bigger expression into smaller, more manageable ones. And we've had situations like this before. We can go ahead and solve for x because there is only one x here. We just have to take the square root, which means we need to have a plus or minus. And the square root of 4,489 is 67. So we get 3 answers here. We get 3 answers, 0, 67, and negative 67. We do have to check our answers, though. It turns out that in this problem, it's pretty clear which one is the bad solution. And it sticks out a lot more easily in this problem, that it's negative 67, because we are not even allowed to plug that number in. So if we tried to test that number, the calculator will complain that you're trying to take the square root of a negative number. So that immediately already tells you which number is the bad number. You toss negative 67, and then the other two will be fine. So you get 2 answers here, 0 and 67. Some other problems, it's not as easy to see. But this one, by virtue of the problem setup, we were able to determine very quickly which one the bad solution was. Does anyone have any questions about this? If not, I'd like to get through the first two problems of the next section. So that concludes the section on radical equations. And again, the homework for this is due Sunday. The homework for this section is going to be due Sunday. So there's a homework due tomorrow, there's a quiz the following day, and the homework for this is Sunday. So we move on to section, this next section, which is equations of the quadratic type. And this is taking expressions that look quadratic, but aren't necessarily quadratic. They're not in x squared plus x plus number form, but they have a sort of structure to them that we can sort of treat them as quadratics. And so we normally refer to this process as U substitution. So you might have heard of this before, but it's a way to rewrite a problem to where once we replace all the x's with u's, then we have a quadratic in essence. And so I wanted to look at the first two to kind of explain this process, and we'll talk more about it next week. So for problem one, it does look a lot like a quadratic. It's not, because instead of x to the fourth, or instead of, it doesn't say x squared, it says x to the fourth. And instead of minus 29x, it says x squared. So really, it looks really close to this quadratic here. It's not, so that's why we use U substitution to pretty much allow us to treat it as if it were the equation I wrote in red here. So the formal process is by using something called U substitution, which means you need to establish a rule that allows you to convert from x's to this placeholder variable, u. So this placeholder variable u, how is this going to replace the x's? Well, normally the middle variable gives a good idea of this. So u is going to replace x squared. So you might be able to think about that in this problem as well. You might want to foreshadow and think about, what do you think the u substitution in that problem is going to be? And I'll leave that as a blank for now. We'll get to that next. But with this u substitution, this is what allows us to rewrite this problem as its corresponding quadratic form, but notice I'm using u's now instead of x's. So now x to the fourth becomes u squared by virtue of that rule, and then x squared becomes u by virtue of that rule. So all the x's become u's, and now we're looking at it as its quadratic form, which means we can just factor. So there's going to be factoring in this section, but the factoring is not going to be that bad. So what multiplies to give 100 and adds to give negative 29, negative 25, and negative 4. So here we get that u is 25 and positive 4 from each factor. So this is part of the convenience of rewriting a problem using u substitution. It's because the substitution allows us to treat the original problem like a quadratic. But we're not done yet, because u is not what we're solving for. We need x. We don't have x yet. We have u's, which is helpful, but it's not the final answer. So if you try to put 25 and 4 into my math lab, it will not accept it. So instead, what you have to do, the last step you have to do is to reuse the rule that you found. That rule helps you convert from u's to x's. So we found two u values. One of the values we found was that u is 25. So we replace u with 25. The other u we found was 4. So ideally, that gives us two separate equations. One for 25, that is u, and another one that's 4, we replace for u. And now in both problems, we need to solve for x. And in both cases, to solve for x, we need to take the square root, which means plus or minus. So plus or minus the square root of 25, it's 5 and negative 5, plus or minus the square root of 4, that's 2 and negative 2. And so you conclude with actually 4 answers. So your final answer is 4 x values. Happens with a 4 x. So this 4 on the x, well, it's what's happening here. Since u is equal to x squared, what happens if you were to square both sides of this? Then you would get u squared is equal to x, well, 2 times 2, which is 4. So to answer your question, the reason why u squared replaces x to the 4th is because of this rule right here. Normally, this extra step tends to throw people off, so don't emphasize it as much. But you could think about it that way. It's going to be the same with the additional problems as well. But that's what happened to the x to the 4th. X to the 4th got replaced by u to the 2nd, because we have to switch all the x's with u's. So let's go ahead and look at problem 2, and that'll be it. So same idea, it's really close to a quadratic, but we don't have the right exponents, which is why we have to use u substitution. So the u substitution, so generally the middle variable will help us in determining this. And by going off of this, x to the 6 is equal to x to the 3 squared. Again, you don't have to think about this way, but it tells you how the x to the 6 becomes u squared. But from here, so now x to the 6 is u squared plus 63 u minus 64 is equal to 0. So in other words, once we replace all the x's with u's, we can utilize the underlying quadratic type, which means we just have to factor. Seems to be u plus 64, u minus 1 is equal to 0, which means that u is equal to negative 64 and positive 1. But u's are not good enough. We need x's. So we need to bring our rule back. And this rule tells us how to convert from U's back to X's. So one of the U's we found was negative 64. The other U we found was 1. And from here, all we have to do to get X by itself is take the third root to get rid of the third power. So the third root of negative 64 is negative 4. The third root of 1 is just 1. We do not need a plus or minus for the third root. That's only for the second root and the fourth root. So only for even roots. For odd roots, we do not need to apply a plus or minus. Other than that, that's all I have for today. If you have any questions, you can go ahead and ask me now. I'll stick around a bit. Other than that, have a good day.
Do good on the exam. I got would that help have me end up dropping a class or something?
So repeat the first part of your question.
Like I didn't do good on the exam.
Well, the exam, that first assessment's only 6% of your grade, which isn't a big deal. It's how you do on the midterm. So the midterm is really going to make or break your decision or your status in the class moving forward. So the assessment, it doesn't really matter too much. So the midterm is what you want to do well on.
All right.
Yeah.
Thank you.
Yep.